Thank you for coming early in the morning. Okay, so today I'm going to be talking about a project which is joint with Fumiaki Suzuki from Leibniz University Hanover. And so I guess first, the structure of the talk is first, I know the title is a mouthful, so I'm going to like define these objects in the title first, then try to motivate them, and then talk about rationality questions. And so since we're dealing with quadrics throughout, we're assuming the characteristic is not equal to 2. Right, that notation board is saved for later. I will say the notation before, like in addition to that square on the top. Okay, so just to start off with an introduction, right, so just to define the objects, so we're going to be dealing with a pencil of quadrics. So maybe in equations, this is just given by Q0, Q1 plus T1, Q2 is equal to 0, where the T's are the coordinates on the PIs. And so the base locus of this pencil is going to be x equals Q1 intersect Q2. And so maybe we'll assume these are quadrics inside P of capital N. And so throughout, we're going to be assuming that x is smooth and it's of codimension 2.
Sorry, what is Q again?
Curly Q?
There's a map from Q to, yeah, curly Q.
Yeah, sorry, Q is like the total space of the pencil, of a pencil of quadrics.
Thank you.
Yeah, so it's just a projection onto the T coordinates. Okay, great. And so what we're going to be interested is linear spaces on the space locus X. So the notation is going to be at R of X. This is the so-called Fano variety of R planes and X. So this is called Fano because Fano studied them. There are sometimes Fano varieties. And so this is something which lives inside the Grassmannian of R planes on Pn. So this is some sort of Hilbert scheme parametrizing R planes on my X. And so in particular, the K points of this are the R planes on X that are defined over K. And so maybe one fact is that, so these objects have been studied. So fact is that this is non-empty as a scheme if and only if R, well, you can't have negative R, but the maximum dimensional linear subspaces are going to have dimension floor of n over 2 minus 1. And then another piece of notation I want to introduce is that, so if n is odd, right, n is equal to 2g plus 1. So in this case, we have a genus G hyperelliptic curve C, which is associated to the pencil, and so in particular C, or so more precisely, C is defined by y squared is equal to minus 1 to the G plus 1 determinant of T times M1 plus M2, where Mi is the symmetric matrix corresponding to the quadric Qi. So this is okay because we're in characteristic not equal to 2. Okay, so this is the notation that I wanted to set. Right, so I've just repeated the notation in this box. So throughout the talk, it's going to be the same notation. So X is always going to be a smooth complete intersection of 2 quadrics, and even n is always going to be 2g, odd n is always going to be 2g plus 1. So I've picked these choices for n in the even and odd case so that the floor of n over 2 is the same in each case. So just replacing like n as above, or like in the above fact, so the maximal R for which this scheme is non-empty is going to be G minus 1. So these are going to be called the maximal linear subspaces on X. The second maximal ones are G minus 2. And the C is always going to be the same hyperelliptic curve when n is odd. So that's just fixing some notation. Okay, so far I have not attempted to motivate any objects. I've just given some definitions. So for the definitions, clear? So I just want to give a few pieces of motivation for why we study X and FR of X. Okay, so maybe the first one, so the first piece of motivation, so if K is the number field, for example, Q, then it's an interesting question to study what are the K rational points of X, right? So in many senses, this is the most basic affinity equation, which is not solved. Right, this is just two like integer solutions to two simultaneous quadratic equations. So maybe more precisely, so what's expected is that, so for n at capital N at least 5, so dimension at least 3, the local to global principle is expected to hold. And so this is known in for n at least 8 by paper of Coley, Tillen, Sensuk, and Swinerton Dyer in 87. And then it's also known for n equals 7 by Keith Brown in 18, and recently Coley Tillen gave a different proof. But for n equals 5 and 6, this is not known unconditionally. And maybe just to remark, so for n equals 4, this is a degree for a del Puzzle surface, and we know that the local to global principle fails for those. So this is one motivation. Right, okay, and so a second motivation I just wanted to say, so in the odd dimensional case, so this board doesn't go higher. So if n is equal to 2g plus 1 is odd, so there's a deep relationship between this hyperelliptic curve C and X, or more generally, the linear spaces on X. So I guess I'll try to start writing some of this here. So maybe one first example is over C. Bandel and Orlov showed that if you take the derived category of X, the derived category of the curve sits inside of it. So they constructed a semi-orthogonal decomposition. X and OX 2G minus 3. So this is one example. And so, this the relationships sort of has many other carnations. And so maybe more generally over any algebraically closed field of characteristic not equal to 2, there's an interesting relation with these varieties of linear spaces. So maybe it was first observed by they, but maybe the best known reference is Miles-Reed's thesis, is that this variety of maximal linear subspaces, so Fg minus 1, this is isomorphic to the Jacobian of this hyperelliptic curve over the algebraic closure.
So in Bundel's result, everything is essentially smooth, right?
Yes. Yeah. Sorry, like everything you mean X.
And C.
Yes.
Okay.
Yeah. Yeah, smoothness of X will imply smoothness of C.
Oh, okay. Good.
Yeah, you can, yeah. Okay. Okay, and so this is something about the variety of maximal linear spaces, but for the other varieties of linear spaces on X, there's a deep relationship as well. So Basal and Ramanan proved that if you take the variety of second maximal linear spaces, so this Fg minus 2, this is isomorphic to the moduli space of rank 2 vector bundles on the hyperelliptic curve C with fixed odd determinant. And then furthermore, for lower R, so for R less than G minus 2, there's a further moduli interpretation where you add some more adjectives to the vector bundles. So then for Fg minus, or for Fr, xk bar R is minus 3. Okay, so these are some motivations. I'm just going to continue to try to give more motivations. So since Right, so one of the main focuses of this talk is going to be what happens over algebraically, non-algebraically closed fields. And right, so in the case where n equals 2g plus 1 is odd and k is not equal to k bar. So in this case, the fg minus 1 has again been studied. So this is a torsor under the Jacobian. And maybe I just want to mention this since it's related to one of the talks yesterday. Which torsor is it? It's pick 1/2 by work of Wang. And right, so just to give one application to number theory, so using this torsor structure over non-closed fields,
Pick 1/2.
yeah. So it's a torsor under this thing, and then in the Rationality group, 2 times this is pick 1.
Oh, okay.
Yeah.
This doesn't define it uniquely, right? I mean, sometimes something is something else, then.
Yeah, that's right. Well, yeah, but I guess it is a pick 1/2. Yeah, so one application of this is that so using sort of the structure of this torsor, Bhagava Gross Wang showed that so if you fix genus G at least 2, so then a positive for a positive proportion of locally soluble genus G hyperelliptic curves, they showed that pick 1 C has no k points, i.e. the curve has sorry, maybe I should just say q points, i.e. C has no k points for k over q odd degree extensions. And in fact, what they show is that actually this for a positive proportion, pick 1 is not divisible by 2 in the T-Schaffer-Rayleigh group. So this is one number theoretic application to this, or of these linear subspaces. And so then finally, okay, I'm going to write a 4th motivation on the bottom of this board. So this is back to algebraically closed fields, but maybe just to mention something in the even case, since these last 2 applications were in the odd case. So over the field k equals c, so there's also a moduli interpretation for this variety of g minus 2 of x over c, which is due to Casagrande. So she showed that this is a certain moduli space of certain rank 2 vector bundles on P1 with some prescribed data at certain points. And then furthermore, the birational geometry of this space was studied by Rahuja and Casagrande. They showed it's like similar to the birational geometry of DP4s in many ways.
What is X subscript C?
Oh, sorry. Okay, maybe if X is over C, I didn't need to write C. I think I was just like emphasizing that the field is C. Yeah. Okay, so those are some motivations. And so then finally, I'm going to give the last motivation, which is the most related to the title of the talk. So, okay, so this is for rationality questions. So definition, just to make sure everybody is on the same page. So variety Y is said to be k-rational with an emphasis on the k. This is defined to mean there exists a birational isomorphism between Y to projective space of dimension Y defined over K. So one thing you can notice is that that if Y is K-rational, then it's geometrically rational, i.e. the base change to the algebraic closure is K-bar rational. However, the converse fails in general. So for example, the pointless conics over R, which we also saw in yesterday's talks, this is an example of a geometrically rational variety, which is irrational over the ground field. And sort of, so for in dimensions at most 2, rationality, so K rationality of geometrically rational varieties is understood well. Is understood. But in dimension 3, there's very much known in general. However, one of the first, like the first none,
Is understood, what do you mean by is understood?
I mean, like, so if you have like, okay, so in dimension 1, it's rational if anyone has a point, and then in dimension 2, there's a criteria for a geometrically rational surface to be rational over the field K. Like, so in dimension 2, so if assume S is K rational,
Yeah, I see what you mean.
yeah, and then assume it's minimal, then like there's the degree and point, yeah. So like there is a criteria, maybe like, yeah, maybe it's not like so easy to check in explicit examples, but there is a criteria. So sort of in dimension 3, a lot less is known, but the first non-trivial example was due to Hassett and Chinkel first over the real numbers, and then generalized by Benoit-Weinberg to other fields. And the variety they studied is a complete intersection of 2 quadrics inside P5. So furthermore, so maybe this suggests that if you want to study rationality questions over non-closed fields, this class of varieties is sort of a fruitful class to study because there's a lot of geometry that's known about them. Okay, so this is this is the motivation I want to give. So next, going to try to state some results. So, option 2. So the main question we'll be interested in is rationality of these linear spaces or the varieties of linear spaces on our X. And so maybe one first thing you can note is that the maximal ones, F G minus 1 X, are never K rational because they're never even K bar rational. In the odd degree dimension case, you have the Jacobian of this hyperelliptic curve, and it turns out in the even dimensional case, you have a 0-dimensional scheme of length which is greater than 1, so it's not rational. And then over C, or I guess for over K bar in the odd case, the second maximal ones, these are known to be rational over an algebraically closed field by the moduli space interpretation. Okay, so that's one thing that's known. And then another thing which was known before is that so for the lowest case R equals 0 over an algebraically closed field X K bar. So just writing K bar for emphasis, which is F0 K bar, this is known to be rational. If capital N is at least 4, so if the dimension of X is at least 2. So why is this the case? So if you do the numerics, so in this case, it says that the idea of lines on X is non-empty. So that means you have a K bar line L, and then you can project from L to get a rationality construction for X. And so the one thing you might notice is that, okay, so the only reason I said algebraically closed is that I wanted the existence of a point on this variety. So more generally, whenever over any field K, whenever you have a K point on this variety of lines, then X equals F0 of X. This is K rational by the same projection construction. So the first result I want to state is that so with Fumiyaki, we generalize this to arbitrary R. So the first result we prove is that if f r plus 1, x has a k point, then this variety frx, this is k rational. And so away from the previously mentioned cases, this wait, oh sorry, so maybe before saying what's new, so maybe I'll just first immediately give two applications. So one first application is that over an algebraically closed field, any non-maximal variety of linear spaces is maximal or is rational. Right, so this seems to be a new result away from the previously mentioned cases. So in intermediate ranges, unirationality was known for a general one by Debar and Mandeville, but the rationality result seems to be new. And then another application I want to point out was a application to rational points, which was pointed out to us by Lene. So over K, a number field for R between 0 and the floor of n over 2 minus 2. So there's two parts. So the first part is that so the Brouwer mod Brouwer 0 it vanishes, i.e. there's no Brouwer mod in obstruction. So in particular, a conjecture of Lene predicts that the Hasse principle should hold for these FR. And then the second result is that if frx has a k point, then weak approximation holds. So maybe I just want to remark, so these both generalize. For FR of x. Yeah, and previously this was known for x by the same paper in 87, like Lene sense explanation diagram paper. So these generalized results from the R equals 0 case. So I just wanted to mention this because this first application is birational geometry, and then the second one is number 3. So I felt like it was fitting for this conference. Okay. Great. And so in my remaining few minutes, I want to focus more on K rationality results for these varieties FRs. So maybe one question one can ask is that, okay, so in theorem 1, we get one rationality construction for these varieties. So question, does the converse hold in theorem 1? i.e., is this the only rationality construction? So it turns out that this the answer to this question was already known to be no. So answer to question on other board. No, so this example is due to Lene. So this is for n is equal to 4 and the field of real numbers. So to construct this example, first we take S a quadric surface inside P3 of R. So this is a quadric with real points and no real lines. And so then you take X to be the blow-up of this quadric surface along a complex point, its complex conjugate, another complex point, and another complex, and the complex conjugate of this other point. So this is degree 4 or degree 8 del pezzo. So this is a degree 4 del pezzo surface. And so this embeds as an intersection of two quadrics. So this is R rational because S is rational, but it has no real lines. And then in fact, for any even dimension, Hassett, Kolar, and Schinkel construct examples for even and at least 6 that have the property that they are rational, but they don't contain any real lines. However, there is sort of one special case in which this question has a positive answer. And so that's the aforementioned threefold case. And so what happens in the threefold case is that x inside P5. So what Hassett, Chinkel, and Benoit Wittenberg show is that f1 of x has a key point if and only if f0 of x plus x is k-rational. And so maybe just to observe some numbers in this case. So in this case, n is equal to 5. And what they show is that f g minus 1 has a k point if and only if f g minus 2 x is k-rational. So I'm going to call this condition star. So if this question fails, then maybe we can ask this more specific question instead of just for all r, just focus on the case of r equals g minus 2. So maybe a modified question. Does this star hold? So one direction always holds by theorem 1. So we're just asking about the converse direction. So I think this is the last thing that I want to say. So then it turns out that this has very different behavior depending on the parity of n. So it turns out that when n is even and when n is odd, we have very different behavior. So first, if you just check the numerics for n equals 4, this is exactly the numerics in this example. So k equals r. This is no by the example of Kohler-Tlen. And so then what Fumiaki and I prove is that for any n at least 6 even, k equals r. No, this is theorem, I guess, theorem 2. And the case where n equals 5, any k, this answer is yes by the result of Hassett and Chinkel and Benoit Wittenberg. And so then what we prove is that we have a partial converse for n at least 7 odd. And it's a partial converse because it differs by symmetric power. Okay. So I think I started 2 minutes late. So can I take, okay. So I just want to say, like, very briefly, some ingredients that go into the proof of this. And then I'll stop. Yeah, so I won't go too much into detail, but maybe since this is connected to some of the future talks this week, I wanted to mention some of the ingredients. So, okay, so what goes into this? So ingredients. So one ingredient is, so what we study is we study the hyperbolic reductions. Of the pencil. So the original pencil curly Q. So more specifically, if we have an R plane on X, then we can take the hyperbolic reduction with respect to this R plane. So we can produce a lower dimensional quadric fibration, which I'll denote B of R from curly Q R to P1. So this is a lower dimensional quadric fibration. And then sort of the birational description we prove, which is useful, is, I guess I'll call this theorem 4. So assume that we have an R plane so that we can define this hyperbolic reduction. So then we show that FR, this variety is K birational to the R plus 1 symmetric power of the total space of this hyperbolic reduction. So the total space of this lower dimensional quadric fibration. Okay, and right, so that's one thing we use. Another ingredient is sort of a fact about quadratic forms, which we learned about in the paper of Hassett and Chinkel. So this says that the variety that you have an r+1 plane on X if and only if this VR, so this is the same VR, this has a K-section. So from these, you can sort of see how we prove theorem 1, because once you have a section, then this total space is rational, so then symmetric power is rational. Okay, and then finally, I just want to say two things about the even and odd dimensional cases. So ingredient 3, if n is even, okay, so when we study these g-2 things, we're studying this hyperbolic reduction g-2. So this, I think it turns out to be a surface. And we use some criterion for surfaces. So maybe I think this will be in the next talk. At least it was in the abstract. So there's some criterion for real surfaces. And then finally, in the case when if n is odd, then the dimension of this Q of g-2 thing, this is a threefold. And so then what we use is the so-called intermediate Jacobian Corsair obstruction developed by Hassett, Chinkel, and Ben Lindbergh, which I will advertise. I think this will appear in Bianca's talk on Friday. So this is just sort of an overview of the results and some of the ingredients in the proof. Thanks very much for your attention.